Good morning, everyone. I'm Will Dawn, an engineer from Think Tank. We are going to talk about control valves, not from a catalog perspective and not from a sales perspective, but from an engineering perspective. Before we discuss valve types, sizing equations, or selection rules, we must first answer one fundamental question. What does a control valve really do in a process control system? Because if this question is misunderstood, everything that follows, CV calculation, flow characteristics, actuator sizing, will be mechanically correct but engineering-wise wrong. First, what a control valve really is. Most engineers, especially early in their careers, think of a control valve as a valve that opens and closes automatically. That definition is incomplete, and in practice, it leads to bad engineering decisions. A control valve does not exist to allow flow. It exists to restrict flow in a controlled and repeatable manner. From a physical standpoint, a control valve is the only continuously adjustable energy dissipating element in a control loop. Think about this carefully. Pipes are passive. Sensors observe. Controllers calculate. Only the control valve physically consumes energy on purpose. The pressure drop across a control valve is not a design flaw. It is the price we pay for stability. Without intentional pressure drop, the process cannot be stabilized against disturbances. So when you hear someone say, pressure loss across the valve is wasted energy, that statement is only half true. Yes, energy is lost. But without that loss, control is impossible. This is the first mindset shift you must make as a control valve engineer. Second, the control valve inside a control loop. Now let's place the control valve into a typical closed-loop control system. Every control loop has three essential elements: a sensor, which measures the process variable; a controller, which calculates the control output; a control valve, which physically changes the process. Here is the engineering reality that many people learn the hard way. A sensor can be perfectly accurate. A controller can be perfectly tuned. But if the control valve cannot move precisely, repeatedly, and with enough force, the loop will still fail. This leads to an important rule used by experienced engineers. When a control loop becomes unstable, do not adjust the PID first. Check the control valve first. Why? Because the control valve is where software meets physics. Algorithms are ideal. Fluids are not. The valve must deal with friction, fluid forces, erosion, corrosion, pressure changes, and mechanical wear continuously for years. That makes the control valve the most stressed component in the entire loop. Third, why control valves are often the root cause of control problems. In real plants, most long-term control problems are not caused by bad tuning. They are caused by excessive friction in packing, incorrect valve sizing, wrong flow characteristic, valve operating too close to fully open or fully closed, trim damage due to cavitation or erosion. These problems do not show up in simulations. They show up after months or years of operation. This is why a control loop may work perfectly during commissioning and slowly degrade over time. The controller did not change. The process did not change. The valve did. As engineers, we must accept this reality. Control performance is limited by the mechanical health and design of the control valve. This is why Think Tank treats control valves not as accessories, but as core control equipment. And then, typical control applications. Same valve, different demands. Control valves are used in many applications, but not all applications demand the same behavior. Flow control requires predictable response under changing pressure conditions. Pressure control often pushes the valve toward critical flow, noise, and vibration limits. Level control experiences continuously changing system pressure drop. Temperature control involves large time delays and process inertia. A valve that works well in flow control may perform poorly in temperature control. A valve that survives pressure control may be oversized for level control. This is why valve selection must always start from process behavior, not habit. Later in this training, we will break down each application and show how valve type, sizing, and characteristics must change accordingly. Let me close this lesson with 3 key takeaways. A control valve is not a passive component. It is an active energy dissipating control element. In a control loop, the valve determines whether the controller's decision can physically be executed. Many control problems originate from valve design, sizing, or condition, not from PID tuning. If you understand these 3 points, everything we discuss in the following lessons will have a solid foundation. In the next lesson, we will clearly define which valves are controlled valves and which are not, and why confusing them leads to serious engineering mistakes.